Hello friends and welcome at my channel. I'm still kind of switching between two languages, German and English. I also teach some mathematics in Russian as well, but not at this channel. I also have another Russian channel where I'm also doing some videos about my traveling. But well, we will see what is the best language to work with. Maybe I'll kind of keep two languages on this channel, which is also, I think, nice because you can also kind of learn some mathematics for about continuity in German language and then compare kind of or try to understand something. It's always nice to speak one more language than none. So I just advise you to learn more and not only mathematics. And today I'm starting a new kind of playlist about combinatorics, all right? And we'll do some basic stuff which I would also like to apply in my playlist in induction with binomial coefficients. So the basic idea today is to do combinatorics and to explain to you guys where the binomial coefficient is coming from. All right, so let's give it a go. First of all, let us see how many different permutations of three different symbols do we have. So if we're talking about A, B, and C, how many different words can we produce out of those three symbols? And their answer is, this is exactly 6, all right? So we also have ACB, we also have BAC, BCA, CAB, and CBA. No more possibilities are given. As I was teaching at the university, I was asking my students, if you can find the 7th possibility, I'm just giving you 20 euros. And you can imagine Monday early in the morning, like everybody's asleep, and then all of a sudden the whole room is becoming silent, and everybody's asking, what did he ask? What's the money for? And they were looking like for the solution, and after like 10 seconds, 20 seconds, nobody found it, and said, oh, there are only 6. I said, I knew, and I'm picking money away. So that's the story. But the thing is, they were awake, you know. So this is a good reasoning to keep your attendance awake. All right. So can we make a picture about those 6 possibilities? Is it possible to kind of project it on the board and to see how those 6 possibilities are being made? Yes, we can. Look at this. If we are here, in order to pick, so whatever letter you decide to pick as the first one, it doesn't necessarily have to be the letter A. Let's say we want to pick B. In order to place B, we have 3 slots at the very beginning. So it could be here, it could be here, or it could be there. There's 3 possibilities that we could have, all right? And the thing is, once I picked the first letter, once I placed the first letter, I only have 2 more possibilities for the further 2 letters, all right? So for the second letter, in the case we placed B at the first place, like here or here, let's say the second letter would be A. For this letter we have 2 or 3 in this case, or 1 and 3 right here, or 1 and 2 right there. And once we place the first letter and the second, for the third letter, there is no choice anymore. We have to take what we have. So 1, 2, only 3. And you see, B, A, for C, there is no choice. It must be there. 1, 3, 2. 2, 1, 3. 2, 3, 1, 3, 1, 2, and 3, 2, 1. So as you can see, at the end, we have 6 different goals where we can end up, and this is exactly the projection of the picture what we see right here with 6 different words. So this is nice to see this way, all right? So first of all, 3 possibilities for the first letter times 2, because behind this one, for example, there are 2 more options, and behind those 2 options there is only 1. So this is 6. All right. Now let's go a bit further and let's see what will happen if we have 4 different letters, A, B, C, and D. What will happen there? Well, you see, the thing is, it's getting bigger, obviously. I'm not going to write them down. It's a big number. It's like 24 different outcomes. But let us understand why they are 24 different outcomes, all right? So, the thing is, we are right here, and the first letter can be placed at the first place, at the second place, at the third place, or at the fourth place. Let's say we pick the letter C to be our prime letter, and we would like to place this at the second place, all right? So this is at the second slot right here. So how many different places do we have to choose from in order to put the second letter? And the answer is 3. After that, we could pick first slot, third, or the fourth. All right. After those 3, we can go on and we can take 2, as you can see. So there would be, we have already 2 and 1, so there is 3 and 4 to choose from. 2, 3, 1, and 4, 2, 4, 1, and 3. And after we've done that, there is no choice anymore remaining because we already have 3 letters put inside, so there is only 1 slot remaining. 2, 1, 3, only 4. 2, 1, 4, only 3. 2, 3, 1, only 4. 2, 3, 4, only 1. 2, 4, 1, only 3. 2, 4, 3, only 1. There are 6 different outcomes. Wait a second, but this was just only 1 possibility at the very beginning. And these are 6. There are 6 here, 6 there, and 6 in here. So we end up at 24. Is that a coincidence? Not anymore, right? Because we have 4 letters, 4 places to choose from at the very beginning, 3 later on, 2, and 1. And this is 24. So the idea is, as you can see, this one branch was actually the whole picture on the left-hand side. So if we have 5 letters, only one way out of 5 will consist of 24 outcomes. And then we will have 120, which is 5 times 4 times 3 times 2 times 1. So that's the story. And that's why we say, well, so important, the Belgian mathematician Lavoisier had a typing machine, and all the symbols were already used in mathematics. Only 2 symbols remaining were the question mark and the exclamation mark, and he took the exclamation mark to take it as the symbol for factorial. So factorial is exactly what we have here. This is, so factoria, factus is a number of possibilities, outcomes. So we have different possibilities to choose from, and we have 4 times 3 times 2 times 1. In German we call it Fakultät. Fakulta is number of outcomes. Factor is rather a product, a factor, which we multiply with. So this is 4 and then factorial. So mathematicians are having fun, and they're saying, if you shout out the number louder, it's going to get bigger. So it's not 4 or something, it's just 4 factorial, which means we just multiply it. All right? Does it make sense? Perfect. So for 5 different symbols, I'm not doing it anymore, but let's consider there are 5 factorial, which is 120 different outcomes. All right, let's move further. What will happen actually if we are dealing with 2 letters still, but one symbol is coming maybe more often? So let's say we have A, B, A. 2 kinds of letters, but no distinguishment between A1 and A2. Well, if we would be able to distinguish the A's, we would have maybe A1 and A2, and if we rearrange them, we would also have A2, B, A1, and you see, this is in ABA. We see no differences between A's, and that's why, well, those outcomes are kind of put together in this one. All right. So another one, BAA, consists also of 2, because if we would have BA1, A2, BA2, A1 would be also all together placed in BAA. Okay, no distinguishing between A's. If we rearrange the A's, we see no difference. All right, so obviously there is less than 6. We had 6 at ABC, you remember that? And in this case, it's only 3, because one last possibility that we haven't discussed is AAB. That's the story. All right, so the thing is, 6 we could have, 3 we do have. So let's see. So 3 is a divisor of 6. Nice to know. And there are 2 ways to permutate, to rearrange the A's without seeing it. Somehow 3, 2, and 6 are maybe connected, right? Okay, let's move further and see what will happen if we have doubled A, double B. What will happen here? Well, you see, if we have doubled A and double B, we would have 4 factorial or 24 different outcomes if the letters would be distinguishable, which they are not. And now let us see, we kind of try to generalize it further. Let us see what will happen here actually if we just look at only this possibility, doubled A, double B, and we are trying to figure out how many different outcomes are already actually being lost. So let's see, A1, A2, B1, B2. This is what we start with. Then if we would have A2, A1, B1, B2, we wouldn't be able to see that. We wouldn't be able either to see this one, nor that one. So 4 outcomes that would be given, if they would be distinguishable, are all together in this one. And now let's think. We would have 24. One such possibility kind of eats 4 away. Okay, it's cutting away. So 24 divided by 4 gives us 6. So that means there should be 6 possibilities of this kind. Is it correct? Well, let's see. Let's figure out. I'm claiming there are only 6. So AABB, the first one, A double BA, the second one, ABAB, the third one, and now the same with B's. BBAA, BABA, and B doubled AB. I got 6. I got no more. And now it makes perfectly sense because we would have 24. We do not have because the letters are repeating. We have 2 possibilities to replace the A's and 2 possibilities for the B's. Now let's see, maybe there is a kind of a pattern that we can recognize. 4 factorial, and we have to divide A's and B's that are repeating. And this is how we come up with, so 4 factorial is 1 times 2 times 3 times 4. Normally we write it down as the highest factorial in the denominator, which is in this case not important because both cases we have 2. 2 factorial is also 2, bam bam, and we are at 6. So there we go. All right, and now let's see one more example with triple A and double B, and now things should be more clear. So if we have 5 different letters, we would have 5 factorial, which is 120, but we have 3 factorial possibilities to permutate the A's, and we have 2 factorial for the B's. So actually the number of outcomes here should be 5 factorial divided over 3 factorial times 2 factorial. Is that correct? Well, let's see. How many letters are really being lost? How many words are being lost? Well, you see A1, A2, A3, B1, B2. Well, if I permutate only the A's and keep the B's the way they are, like A1, A3, A2, B1, B2 here, A2, A1, A3, B1, B2 still in here, A2, A3, A1, B1, B2, A3, A1, A2, B1, B2, and A3, A2, A1, B1, B2. What do I have? What I have is 6 different possibilities that are being lost in here, all right? But I also can rearrange the B's and I would have 6 more. So I really have 12 possibilities that are being lost, all right? In just one of these outcomes. So how many of those outcomes should I have? Well, 120 I would have in total. Each time 12 are being lost, so I should have 10. Is that the number we're going to get here? Let's see. 5 factorial we are writing as 3 factorial times 4 times 5 divided over 3 factorial times 2, boom, boom, bam, bam, and we got 10, which is nice. All right. So let's go even one further step, and let's do the following situation. Let's see if we have, let's generalize it, if we have A's and B's, all right? Have K of those, K times. In total, we got N times the letters, so that would be N minus K times the B's. So if they would be distinguishable, we would have N factorial. They are not. So we are having K times the letter A and N minus K times the letter of B. This is exactly what we've been doing previously. Look at the first example. We have 3 factorial, if they would be distinguishable, 2 factorials for A, 1 factorial for B. 3 factorials, I can write it as 2 factorial times 3 divided by 2 times 1. Bam, bam, we got 3. It was really the number of outcomes. What about here? Well, we've done it already, right? 4 factorial divided over 2 factorial and so on. Now, generally, if we do not know K, but the total number of letters is N, we produce N minus K, so that's the story. All right, so it's so often used in mathematics, combinatorics, statistics, and all kinds of, well, science, that we have a shortcut for this, and we call it binomial coefficient. And American students or UK students name it also N choose R, which makes perfectly sense. N choose R means you have N different outcomes and you have only 2 distinguishable letters, just A and B, male and female, yes or no, 1 and 0, and so on. And so if you tell me K outcomes, so like imagine you have a shelf full of books, and we just want to kind of order this, have to do it at home as well. And let's say we have 5 different opportunities, 5 slots where we can place the books. And if per slot only 1 book is allowed. So this is 1, this is 2, and let's say this is 3. So you see, actually, all of a sudden we are modeling words that we've been doing previously, and we have different words like 5 factorial, if they would be distinguishable, they are not. We have 3 factorial for B's and 2 factorial for X's. We can compute it. We've done it previously. It was 10, right? So there are 10 different possibilities for us to compute it, which is pretty nice. And on the other hand, I can say, well, if I, instead of X, if I instead of B call you the places where no books are allowed, for example, the 3rd and the 4th slot should be empty. And you know, the only way, if they are not empty, they're full, so 2 different outcomes. So I immediately called you also, or told you the 1st, the 2nd, and the 5th should be filled with book. Okay, so that's the story. So we have a kind of symmetry as well. That means N choose K is the same as N choose N minus K. So once again, you want to visit me next week, and I'm telling you, well, Monday, Wednesday, and Friday, I'm totally occupied. I'm totally full with all of my lessons, sports, whatever. So you can only visit me if I'm not telling you about any other days on Tuesday, Thursday, Saturday, or Sunday, right? So telling you 3 days that are not possible, I immediately allow you to choose 1 day which is possible. This is the story we have right here. So N choose K was N factorial divided by k factorial times n minus k factorial. What about here? Well, we have n factorial divided over n minus k factorial times n minus k factorial, as you can see. We are opening the parentheses, and we have n minus n plus k factorial. We're canceling those two, and we get n factorial divided over n minus k factorial times k factorial. Now we can rearrange it, and we are at the definition of n choose k. So this is the proof. All right? Yoo-hoo! Thanks for listening and for watching. One more thing I would like to add here, even though the video is already over 20 minutes. Why do we actually call 0 factorial equal to 1? That's a nice thing. And I could maybe do a separate video, but this kind of bonus, since you've been working so hard listening to me for 20 minutes, 1 more minute will make it. All right, thank you. So let's imagine we have a situation with shelves, with books, and with our slots, and we have 5 slots, and in every slot there is a book. All right, so book, 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 and book. All right, so we have 5 slots and 5 books, and what we see is there's only one possibility for this slots to be full. Just in every slot there is a book. That's it. It should be 1. Okay, it should be 1. Well, but what about our n choose k situation? Well, once again, n choose k, this is n factorial divided over k factorial times n minus k factorial. And well, it's kind of strange here, because if we rewrite 5 choose 5, we're gonna have 5 factorial divided over 5 factorial times 5 minus 5 factorial, which is bam bam 1 divided by 0 factorial. Well, and now we are in a kind of situation what we've been discussing with division by 0. Well, obviously, if you remember, 7 times 0 would be a rectangle with the length of 7 and with the height of 0. So there is no area. If we allow the division by 0, we kind of have to allow, in this case, having area, which makes no sense to us. That's why division by 0 was cancelled, one of the reasons. Also, in order to apply the power rules, at some point we've been discussing why it makes sense to define 7 to the power of 0 to be equal to 1, in order to kind of, well, better describe the reality that we are able to see and we are able to live in. And what about the situation here on the left-hand side? Well, you see, if we're dividing by 0 factorial, the outcome should be 1, because this is what we see, all right? So if I have a pen and I just let it fly, I drop it, it should be flying, okay? It should be flying downwards. Why? Because the gravitational force of the Earth is strong, the mass of the Earth is strong, it's attracting my pen is also attracting the Earth, but it's not comparable, and that's why my pen is flying downhill. This is what I see. If at some point my theory would tell me if I drop the pen and the Earth must be coming up, maybe my theory isn't precise enough, all right? Or I should think about it. And that's the same story. I mean, it should be 1, and the only thing to save it is to define 0 factorial to be 1. Any other choice of this kind would really contradict our theory previously, and we would have to define a special case for 0, like we already have if we divide. We don't want to do this. It makes sense, and 0 factorial is perfectly 1, nothing is wrong. So, would it be working this way? What would be 5 choose 0? If I would say I have no slots, which is empty, what about 5 choose 0? Would it be still the same as we proved previously with this equation hold? Let's see. It would be 5 factorial divided over 0 factorial times 5 minus 0 factorial in the denominator. It would be 5 factorial, 1, 5 factorial, boom, boom, and we would have 1 divided by 1, which is 1. Perfect. Okay. Thank you guys for watching this video. I hope you learned something. I explained some basic ideas about combinatorics, about replacement, and about binomial coefficient. And well, hope to see you in the next videos. Have a good day. All the best. Bye bye.